All right, we are back to this picture again in talking, in relating to the next subtopic. Okay, so back to the single slit here. If we have changed to two slit, as in from 3 to 1, you can see it become clearer now, as in the resolution get better. Okay, so the picture get clearer, you can see more details coming out. And then if let's say your slit is small, then you get even fine details. So now think about that. If we are not just using 2, but we put 3, we put 4, 5, 10, 20, 100, 1000 lines in within that small region, so what do you think will happen? Of course the light gets even more focused, right? So it's like the small band here, it will become even fine, even more fine. Okay, and then a lot more details will be like something like this. Okay, so they become like a very thin line. Okay, and then it's very bright because we have more lines passed through, right? Okay, but the thing is, if you want to squeeze the slit into this kind of small region here, right? Okay, not only you have to make them small, but you have to make them very close. If you make them close together, then the problem is it is going to get wider or bigger distance away. Okay, so that's the logic behind it. So because when you get them closer, then the chance for them to have a path difference of lambda and 2 lambda and all that, it will shift further. All right, so if you can reason this out or understand this or can picture this, then we'll now move on to the next part. Okay, this subtopic is called the diffraction grating. What is diffraction grating? It's a plate, later I'm going to show an example, that we fit a lot of tiny little parallel slits into that. Okay, how does it look like? Hold on. And if we shine monochromatic light, monochromatic here means single frequency. That light only consists of a single frequency. Understand this word, it is always used. Monochromatic light is incident on this plate. A pattern of narrow bright fringe is produced. Okay, let me bring you to the picture. Okay, so what you see here is the one with the black color frame there is the what we call the diffraction grating. So inside, in between there's like a window there. So it's not like a window actually, it's a transparent piece of thing. And inside there, there's a lot of tiny little slits that is arranged so close together that looks almost just transparent. Okay, and then in front here you see the white color thing. Actually this is a source of a laser. So the laser is shining through the window, so-called, and then it hit at the wall behind, at the screen behind, and then you can see that there are 5 little alien light dots there. Not alien, actually it's just the light. So they are very bright because there are a lot of slit, and therefore a lot of lights can pass through, right? So but the thing is, compared to the pattern that we have looked at just now, this one is like it's spread out a bit. That's due to the close distance, and then they are just a few of them. Okay, the others, they could go very far away or they are not visible at all. So later we'll talk about that. Okay, let's go back to that. So here's a picture trying to explain on what exactly is happening. So those slit, right, as the light pass through, you can see those arrows that pass through. If they are able to pass through, then they will meet with those that can give a path difference of lambda. Okay, so if we are talking about the bright fringe, so let's just focus on talking about bright fringe. So they will seek those positions where all of them has the integer number of wavelength in terms of path difference. Okay, so in the middle here always it will be just a bright fringe that we call as a zero order, okay, maximum or central maximum, n equals to 0. And then the one on the top and bottom, we call it both the first order maximum. Maximum means is where a constructive interference pattern happens. Okay, that's called the maximum. And then if you have some more on top, some more higher, then you got second order, third order, fourth order, fifth order with the denoted by the n equals to that number. Okay, so now we want to come to an equation that governs this. So look at the arrow here. Now we jump to the next slide. Okay, so that's like zoom into two slit there. All right, so if the slit is very close together, and as we zoom in, right, we can see that those two lines, they are almost parallel. Okay, those slightly different but can be ignored. And then we focus on the triangle. Okay, here basically the triangle there will enable us to find out their path difference in terms of the distance between the slit and the angle of this triangle. Okay, that's the d sine theta, because it's a right angle triangle. So, oh, sorry. Clear that. Oops, I can't. Never mind. Okay, so d sine theta equals to n lambda. That's what we are trying to tell just now. If we are focusing on the you got that, the constructive interference, that's when they have the path difference of m lambda, right? So n lambda equals to d sine theta for nth order of the maximum. Okay, start with 0, 1, 2, and 3 for the n. Okay, so this is the equation for diffraction grating. So two equations are, the double slit is x equals to lambda DOA. The diffraction grating is d sine theta equals to n lambda for bright fringes. Okay, d is the grating spacing, that's the term for it. Theta is the angle of parallel rays to the horizontal. Okay, that theta, this theta of this yellow triangle is the same as this. Geometrically is the same. Okay, very important. But you don't need to really deduce that. You just know that this theta is also the same as the one that I'm highlighting here. Okay, n is the order of the diffraction, as in the 1, 2, 3 that we mentioned in the slide earlier. Lambda is a wavelength. Okay, so we have one example here. Parallel beam of the monochromatic light is incident. Normally, they will always tell you the case is a normal incidence, because we are not going to talk about the others. It will be slightly different. Second order. So second order means n equals to 2. Our maximum is observed at this 18.9. So it means that if we draw that picture, this is the second order, n equals to 2. Then the theta here is 18.9. That's what it means. Okay, so this is where the diffraction grating in dg. Assuming that the wavelength is this, find the grating spacing. So we need to find the d. So n lambda equals to d sine theta. So n equals to 2, lambda is given, and d is what we need to find, and then we sine 18.9. So remember to change to degree. Okay, then d should be equals to this. Okay, light of wavelength 5.7 10 to the power -7 is incident normally. See, incident normally again on the grating with spacing of this. So again, this is the d. What's the angle to the normal of the first order maximum? So again, we have the n lambda equals to d sine theta. Okay, we are asked to find the for n equals to 1 and for n equals to 2, what is the respective theta? Okay, I think you can try out on your own, see whether I got the answer. I don't have the answer. Okay, so this one will be your assignment question. Okay, so let's say the light that we are trying to shine on the diffraction grating is not just monochromatic, but it consists of the full spectrum of the rainbow. Okay, that means that we'll have couples of wavelengths ranging from red color to violet, right? And you need to remember the range is 400 to 700 nanometers. So in between, you just divide equally, which means that n lambda equals to d sine theta. If the lambda is has a range, that means the theta must have a range. So which means that when they pass through the diffraction grating, right, they are going to not just become one light, but they will split into different position. So like what you see at the bottom here, they will split into the rainbow colors. So center will be a white color, but you will see rainbow color on both sides of it. So certain orders of the rainbow color, sometimes they will overlap a bit. Okay, so it means that it helps to break down the colors. Okay, what is so good about this breaking down of colors? Just like you have the mass spectrometer for chemistry. I think some of you learned about that. Mass spectrometer, we want to find the elements inside a certain specimen, right? So this light spectrometer will break down the lights and see what's inside there. Okay, so imagine that we want to look at some distant stars, and we only get white light. So what happened is that we place this thing, or we point the telescope to that, and then we place the light spectrometer. Then it breaks down the lights there. So when we see the light there, then we are able to analyze what elements are inside these stars. What gas does it have? Okay, if you want to know the details, then we continue to A2 lah. You follow me to A2, then I'll tell you the story behind. Okay, so we'll stop here. So light spectrometer, that is where it divides the light into its color elements. Okay. So why red color diffracted the most? Simple question. You try to answer that. Okay, so spectra seems to fade away as the order is higher, right? So if you look at the picture just now, it fades away. How to find the highest order of the diffracted beam produced? I go back to the picture just now. So you see that it becomes fainter. So if you look at the geometry arrangement here, as you move the telescope to the right and to the left, you will see the one at the bottom here, like the whole thing here. Okay, as you move. So this is in the middle, as here. So as you move to the side, then you will see this to the side. And if you move to this side, then you see it to this side. So the thing is, you cannot move over it, right? You cannot move over it because the light doesn't get reflected. Right? It passes through, but it doesn't get reflected. That means there must be a certain highest order that you can see. Is it 5? Is it 6? Is it 7? Is it just 3? Or is it just 2? Okay, so how to decide that? Then, of course, we make use of the geometry here. That is the 90 degrees. 90 degrees is the maximum of the theta. So once we are able to find the end there, then we should be able to find the boundary of it. Okay, that's what I mean just now. 90 degrees means equals to 1. It must be less than 1. Okay, so let's look at this one. We have the again incident normally. Second order diffracted from a beam form at angle of 40 to the origin direction. What is the highest order? So you are given these two information. When n equals to 2, theta is 40 degrees. So what is the highest order? What is the highest n? Is it 3? Is it 4? Is it 5? That's what it means by that. So let's look at the solution. So from this side, theta equals to n lambda. With the condition of sine theta, 90 degrees you put in, is equal, can put equal, doesn't matter. This one is equals to 1. Okay, that sign is a bit confusing. Alright, so from the information above, we put in the 2 and also the 40 degree, and then we should find the lambda over d, a number that represents that. So after that, we sub this into 1. Okay, we sub this into 1, then we should be able to find a number for the n. Okay, because you know that equals to 1, then you should throw the others to the other side, then you should find a number, for example 3.11. 3.11 haven't reached 4 yet, then you should use round down, as in n equals to 3. Even if it's 3.9, you have to put 3 also. Okay, so n equals to 3 is the highest order. Okay, we have the center maxima, 3 on top, 3 below. That's it. Okay, 3 on top, 3 below. Highest order is 3. Alright. Okay, so that's all for this.